Okay, so in today's lecture, we're going to get started on chapter 6, which is counting and combinatorics. So, right, like it sounds, combinatorics is essentially, from one perspective, the study of how we count things or enumerating different collections. Like, there are plenty of things in mathematics that we want to enumerate. We've done a lot of these, like finding the number of subsets of a set, or finding the number of ways in which a task can be done, or you know, finding the number of arrangements of, I don't know, people or postcards or whatever. Um, so what I want to do today is just start off with a couple simple rules for counting that we use and can apply to some actually quite interesting combinatorics problems. So let's get started. The first one that we're going to discuss is the combinatorics product rule. So essentially what this is saying is the following. Suppose a procedure can be broken down into a sequence of two tasks. And let's say the first task can be done n1 ways, and the second task can be done in n2 ways. Then the number of ways of doing the task, the whole task, then there are n1 times n2 ways of accomplishing the task or accomplishing the procedure. So nothing new. I'm sure that you've seen this idea or this combinatorial rule before. And use it to calculate, I don't know, the number of different outfits if you have n shirts and n minus 1 pants, for instance, and I don't know, n3 number of socks. So basically, yeah, that's another thing to point out. Here, the combinatorics product rule is stated for breaking a procedure into two tasks, but as long as you have some finite number of tasks and each task can be done in n sub I ways, then you can just multiply all of those together and get the total number. So as an example, let's say two employees have 12 available offices. How many configurations are there of putting both of those employees into two distinct offices? And this is rather straightforward. So if we call employee 1, we could say that the first task is finding employee 1 an office. And so there are going to be 12 ways of doing that because there are 12 offices that employee 1 can choose from. Then the second task, after the first task is accomplished, this is number of ways of finding E1 an office. And then the second task is to find E2 an office distinct from E1. So as long as E1 picks some office, then employee 2 will have 11 choices left, number of ways of finding E2 a distinct office. So this product, 12 times 11, which is equal to, I think, 132, is going to be precisely the number of configurations. And how we did that is we broke up the whole procedure into 2 tasks, each of which was easy to enumerate. Okay. Um, let's do another example. Example, how many license plates are possible um, on 6 symbols, which are um, capital letters, and numbers? Okay, so essentially you've got 6 slots, and in each slot you're going to put either a capital letter or a digit from 0 to 9. So let's assume that there are no other restrictions, and so how many, so we have essentially broken this up into 6 tasks, and how many ways are there to choose the first symbol? Well, your options are 26 letters and 10 digits, 0 through 9, so there are 36 ways to pick a symbol that goes in the first slot. And then there are no restrictions about what the next symbol can be, right? I'm not saying that you can't have a license plate that says A. So, for instance, this next one would also be 36 and 36. There are 36 choices for each slot, and so we just get the number of license plates is 36 to the 6th. 36, 36, 36, right? 36 choices for each slot. And they don't depend on anything else, right? Okay, so those are 2 kind of basic examples. Let's do another proof of a fact that I think we've already seen, and let's prove it in 2 different ways. So, example, let's show that the number of subsets of a finite set A is 2 to the cardinality of A. Now, there are lots of ways to show this. I'm going to go through 2. First, I'm going to do induction, because it's always good to practice a little bit of induction. Let's do a base case. Let cardinality of A be equal to 1. Then there are 2 subsets. Of A, the empty set is a subset of A, and A is a subset of A. There are no other subsets for a 1-element set. Okay, and in particular, so there are 2 subsets, and that's the same as 2 to the cardinality of A is equal to 2 to the 1 is equal to 2. So we've proven the base case. Now for the inductive step. So what we're going to do is assume that for sets A such that the cardinality of A is equal to R, number of subsets is 2 to the r. Or yeah, 2 to the r, which is equal to 2 to the cardinality of A. So this is the inductive hypothesis. And now what I want to examine is I want to examine sets of the form set, say, A prime, such that cardinality of A prime is equal to the cardinality of A plus 1, right? The thing that I need to show in the inductive step is that if I assume the thing holds for sets of size r, I need to show that it holds for sets of size r plus 1 equals r plus 1. Now the point is A prime is equal to some set A, well maybe I'll write some set S. So the set A prime is equal to a set S union one element. Let's call it A, right? Given any, so if I take my set A prime with r plus 1 elements, I remove one element, I call that removed element A, and then what I'm left with is some set S with cardinality R. So now I can use the inductive hypothesis in just a moment. So let's consider subsets of A prime. I claim there are two kinds of subsets. Those which contain A and those which don't. Okay? Two kinds of subsets of A prime, those which contain this kind of extra element A and those which don't. So the subsets that don't, the point is we can produce each of these subsets from subsets of S. So the next claim is that for each subset of S, S prime of S, we get two subsets. Of A prime. Namely, if S prime is a subset of S, we get one subset, S prime, as a subset of A prime, and we get S prime union that extra element A as a subset of A prime. So for every subset of S, I get one subset by doing nothing and just saying that that's a subset of A prime, and then I get another subset given by including A with that subset S. So these yield all possible subsets of A prime, because every set which doesn't contain the little element A is some subset of S, and every subset of A prime which does contain the element of A is the data of containing A and then some other subset which we can write as S prime, a subset of S. So these yield all possible subsets of A prime, and so thus A prime has 2 times as many subsets as S. So number of subsets of A prime is equal to 2 times, and now here's where I use the inductive hypothesis, because I know how many subsets there are of S if the cardinality of S is R, right? I use my inductive hypothesis all the way up here. 2 times 2 to the cardinality of S. But 2 times 2 to the cardinality of S is equal to 2 to the cardinality of S plus 1, which is equal to 2 to the cardinality of A prime. This completes the inductive step. Okay, kind of long, but still valuable and interesting. This is how we prove the number of subsets using induction. Now let's use